New York subway has a problem that sounds almost impossible. During the worst storms, engineers have to turn parts of a century-old transit system into something closer to a sealed ship. That is why the city has installed massive flood doors, retractable stair covers, watertight hatches, and fabric barriers strong enough to hold back a wall of water. They are not one continuous gate buried beneath Manhattan. They are a network of defenses placed wherever the surface connects to the tunnels below. And that distinction matters, because the subway's greatest strength is also its greatest weakness. It must remain open to people, air, electricity, maintenance crews, and trains. Yet every opening that keeps the system alive can become an entrance for floodwater. So how do engineers seal a subway without suffocating it, blocking passengers, or shutting the city down every time rain appears in the forecast? And why can even the largest floodgate protect New York from one kind of storm while doing almost nothing against another? The answer begins on October 29, 2012. As Superstorm Sandy approached New York, the subway had already been shut down and trains had been moved away from vulnerable areas. But the storm pushed an enormous surge of seawater into the city. Water crossed streets, climbed over bulkheads, and found thousands of paths underground. At South Ferry, one of the system's lowest and most exposed stations, water rose almost to the ceiling. Tunnels beneath the East River filled. Salt water reached signals, electrical equipment, communication systems, and the third rail that powers trains. When the water finally receded, the damage did not simply disappear with it. Salt remained on cables and metal surfaces, accelerating corrosion long after the storm had passed. The disaster revealed something uncomfortable. New York did not merely have a drainage problem. It had a geometry problem. The subway was built as a vast connected network, and water is extremely good at exploiting connected networks. Most passengers experience the system as a staircase, a platform, and a train. Engineers see a web of entrances, sidewalk vents, access hatches, tunnel portals, pump rooms, and old joints where one era of construction meets another. Every one of them can become a doorway for water. Under ordinary conditions, those openings are necessary. Vents release heat and move air. Stairs move millions of people. Portals allow trains to pass between open air and tunnels. Access hatches let crews reach equipment. Drainage channels collect the groundwater that naturally seeps into underground structures every day. But during a coastal surge, the same network begins behaving like a collection of funnels. Water does not need to break through a tunnel wall if it can simply pour down a staircase. It does not need to crush a station entrance if it can fall through a ventilation grate beside the curb. And once enough water enters one part of the system, tracks and tunnels can carry it toward places that were never directly exposed to the storm. This is why the idea of a floodgate is deceptively simple. The visible job is to block an opening. The real job is to interrupt a chain reaction. Consider a subway entrance in Lower Manhattan. On a normal morning, it must remain completely open. Thousands of people may pass through it. Nothing should narrow the stairs, create a tripping hazard, or require passengers to walk through an industrial doorway. Then, a major coastal storm approaches. Within a limited preparation window, crews need to convert that same open staircase into a watertight boundary. The barrier must span an irregular opening, seal against old concrete, resist debris, and transfer the force of the water into the surrounding structure. That force rises quickly as the water gets deeper. The lower part of a flood barrier carries far more pressure than the upper part because it supports the weight of all the water above it. A gate that looks calm from the dry side may be holding back tons of water on the other side. A conventional steel door can do that job in the right location, and New York uses heavy marine-style doors at some facilities. But subway entrances are rarely identical. Some are narrow, some are wide, some bend around corners, some sit in crowded sidewalks where a permanent swinging door would be impractical. That is where one of New York's strangest defenses comes in, the FlexGate. Instead of relying on a single rigid slab, the FlexGate uses a high-strength fabric barrier reinforced by structural webbing. When it is not needed, the material is stored compactly near the entrance. Before a coastal storm, crews pull it across the stair opening and secure it to the surrounding frame. Calling it fabric makes it sound delicate. It is not. The design behaves more like a flexible dam. The membrane spreads the water load across the webbing and into the anchors around the opening. Because the barrier can bend, it can fit locations where a rigid metal gate would be difficult to store or deploy. The material also solves a logistical problem. A flood defense is useful only if crews can close it before the water arrives. Older temporary systems often required workers to retrieve separate metal beams or panels, transport them to each location, and assemble them in the correct order. A barrier stored at the point where it will be used removes several chances for delay. In an emergency, simplicity is an engineering feature. But flex gates are only one part of a much larger toolbox. Some stairways receive retractable covers that close, like enormous horizontal lids. Sidewalk vents get removable or mechanical covers. Watertight hatches protect access points. Marine doors isolate electrical rooms, and larger barriers defend tunnel portals and rail yards. Each device is shaped by the opening it must defend. There is no universal gate because the subway itself was never built from one universal design. Different lines were constructed by different companies in different decades using different dimensions and materials. A barrier that fits one staircase may be useless 2 blocks away. Even the surrounding concrete matters, because a perfect gate attached to a weak wall simply moves the failure somewhere else. So before engineers install a barrier, they study the route that force will take from the water, through the frame, and into the surrounding concrete. They also search for any path around the gate, a cable opening, a ventilation duct, or a crack nearby. This is the unglamorous part of flood engineering. The most dramatic object may be the gate, but the smallest unsealed gap can decide whether it works. After Sandy, the Metropolitan Transportation Authority began hardening thousands of vulnerable openings. The work included doors, covers, sealed penetrations, stronger drainage, elevated equipment, and flood walls around critical yards. South Ferry alone required hundreds of millions of dollars in repairs and protection. The scale of that investment makes sense once you understand what is behind the barrier. A flooded platform is disruptive. A flooded signal room can disable an entire section of railway. A damaged power system can keep trains out of service after the tracks appear dry. And salt water can turn a short emergency into years of repair work. That is the first major payoff of these giant gates. They are not simply protecting empty tunnels, they are protecting the hidden systems that make every train movement possible. But now the story takes an important turn. The defenses built after Sandy were designed mainly for coastal flooding, a storm surge that rises from the ocean and rivers, usually with enough warning for the transit authority to shut parts of the network and deploy barriers. New York is also facing a different threat. Torrential rain can fall far from the coastline, overwhelm a neighborhood in minutes, and flood stations that were never considered coastal. A coastal surge approaches from the edges of the city. A cloudburst can appear almost anywhere above it. That difference changes the engineering. A large deployable gate works when crews know where the water is coming from and have time to close the correct openings. It is much less useful when intense rain suddenly turns several streets into shallow rivers during the evening commute. Closing every entrance whenever thunderstorms are possible would make the subway unusable. And even if every staircase could be sealed instantly, water would still have other routes. The subway has its own drains, sump pits, and pump rooms. A sump pit is simply a low collection chamber where water gathers before pumps move it away. Under normal conditions, this system handles groundwater, small leaks, and ordinary rain. The pumps usually send that water into New York City's sewer network. That arrangement works until the sewer is already full. During extreme rainfall, the subway and the streets are effectively asking the same underground pipes to accept more water at the same time. When the sewer cannot take it, the pumps lose their destination. Water can collect in stations, flow along the tracks, or even push backward through connected drainage lines. At that point, the problem is no longer contained inside the subway. It belongs to the entire city. This is why a few additional steps at an entrance can sometimes matter as much as a giant gate. Raising the edge of a stairway creates a small permanent barrier that works without a crew. Elevated ventilation grates keep street puddles from draining directly underground. Cleaner track drains allow water to reach pump rooms instead of spreading along the rails. These measures are less cinematic, but they protect the system every day. The same logic applies to pumps. A larger pump sounds like the obvious solution, but capacity alone is not enough. The pump must have reliable power. Its controls must remain above the flood level. The discharge pipe must lead somewhere that can still receive water. And crews must be able to maintain the equipment inside a station that operates almost continuously. Flood resilience is not one machine. It is a chain, and every link has to keep working under the same storm. The consequences become serious before a tunnel is completely submerged. Trains receive electricity through the third rail beside the tracks. If water rises near energized equipment, service may have to stop for safety. Signals and switches can also fail. Passengers can be stranded even when the platform itself is not underwater. That helps explain why the subway can shut down during a storm that leaves much of the city above ground looking merely wet. Underground, a small rise in water can be enough to cross a critical electrical safety limit. Hurricane Ida demonstrated the new problem in 2021. More than 3 inches of rain fell in a single hour in parts of the city. Nearly the entire subway network was forced to stop, and passengers had to be evacuated. The coastal barriers installed after Sandy had not failed at their intended job. The water was attacking from a different direction. That distinction is easy to miss, but it is central to New York's next phase of construction. The next phase combines deployable coastal defenses with measures that are always active: raised entrances, higher vents, sealed leaks, stronger pumping systems, and better protection for the places that repeatedly flood during heavy rain. The Metropolitan Transportation Authority's current capital program targets additional stormwater protection at 20 of the most vulnerable stations and yards. It also calls for closer coordination with the city agencies that manage streets, catch basins, and sewers. Because the subway cannot solve surface flooding by itself. Suppose a station entrance is perfectly protected, but the intersection around it collects water faster than the street drains can remove it. The entrance may remain dry while nearby buildings flood, or the station pumps may work correctly, only to discharge into a sewer that is already overloaded. The durable solution has to begin before water reaches the turnstiles. That can mean larger sewers, underground storage, better maintained street drains, absorbent parks, restored wetlands, and street designs that direct runoff away from vulnerable openings. In other words, protecting the subway sometimes requires rebuilding the city above it. That is the deeper reason New York's floodgates are so interesting. They look like defensive walls, but the engineering philosophy behind them is not simply to build higher walls everywhere. The real strategy is layered. Block predictable coastal water at the largest openings. Reduce the rainfall that reaches the system by raising entrances and protecting vents. Move the water that still gets inside through drains and pumps, while keeping power, signals, and communication equipment dry. Then, design the system to recover quickly, because no realistic city can guarantee that every drop of water will remain outside forever. That last point is important. The goal is not to make the New York subway perfectly waterproof. It is too large, too old, too connected, and too essential for that promise, to be honest. The goal is to prevent ordinary flooding from becoming a system-wide failure and to prevent a rare disaster from destroying infrastructure that takes years to replace. So, why are New York engineers building giant floodgates around and beneath the subway? Because a modern city depends on an underground network that was designed for a different climate, the gates create temporary boundaries inside a system that normally has none. They buy time, protect critical equipment, and stop floodwater from turning connected tunnels into a path for destruction. But the gates are only the visible part of the answer. The full defense is a coordinated system of barriers, raised openings, drains, pumps, sewers, and surface infrastructure. New York is not trying to defeat water with one enormous door. It is learning where to block it, where to redirect it, where to store it, and when to let the rest of the city help carry the load. That is how an old subway begins adapting to a new climate. If you enjoy seeing how hidden infrastructure keeps modern cities alive, subscribe to Parallax Depth. I'll see you in the next one.